Hello everybody, welcome into another lesson. So today we are going to talk about trapezoids. This is the last type of quadrilateral we're going to talk about. So what is a trapezoid? A trapezoid is a quadrilateral that has only one pair of parallel sides. So here's a picture of a trapezoid. You have trapezoid ABCD, where AB is parallel to CD. The two parallel sides are called the bases. So AB and CD are both the bases of the trapezoid. And then you have AD and BC, those are called the legs of the trapezoid, the non-parallel sides. So that is generally what a trapezoid is. There are two theorems today. We're going to prove the first one. The second one is going to be just simply some exercises with algebra in it. So the first theorem states the base angles of an isosceles trapezoid are congruent. So the theorem we're about to prove here and learn is that the base angles of an isosceles trapezoid are congruent. Okay, so what's an isosceles trapezoid? An isosceles trapezoid occurs when the legs are congruent to each other. So if AD were congruent to BC, you would have an isosceles trapezoid. By this theorem, the base angles D and C would be congruent to each other. So that's really all that's saying. It's kind of almost like an isosceles triangle. We know in an isosceles triangle, per the isosceles triangle theorem, that if opposite sides are congruent, then the angles opposite those sides are congruent. It's the same kind of idea with an isosceles trapezoid. In fact, you could almost call this the isosceles trapezoid theorem if you wanted to. That would actually make sense, the isosceles trapezoid theorem. So there is that. Now let's go on to our proof. We only have one proof today. All right, so we are going to be given, let me draw the diagram here. I should probably make this a little bit bigger, huh? Let's make this just a little bit bigger. All right. Well, once again, we'll call this trapezoid A, B, C, and D. So what are we given here? Of course, we got to put the parallel markers since it's a trapezoid. That means AB would be parallel to CD. Okay, so here's what we've been given in this particular case. We are given that we are just given trapezoid A, B, C, D with AD congruent to BC. So we are given trapezoid ABCD with AD being congruent to BC. So we can actually, if we want to, why don't we go ahead and mark those as congruent? That's going to aid us here in just a minute. What we have to prove is that angle C is congruent to angle D. So in other words, we're proving the theorem that we just learned, that the base angles of an isosceles trapezoid are congruent. Well, we already have that this is an isosceles trapezoid. We just got to prove that these two angles are congruent. So let's go ahead, we'll set up our columns. This actually won't be that bad of a proof, not at all. Statements and then the reasons, okay. Now what do we have here? So let's start with our given information for statement 1, that we have trapezoid trapezoid ABCD with AD being congruent to BC. That, of course, is given information. That's the reason for the first statement. Well, where do we go from there? You're probably wondering, where do we go from there? Remember how I said before, if you ever need to, in your diagram, you can draw what's called auxiliary lines, which are lines that aren't really there, but they do help. So what you want to do is draw a perpendicular line from A down to CD. This will form a right triangle, and then draw one here from B down to CD and form another right triangle. All right? We will call those points where A meets CD is perpendicular to it X. We'll call the point where B meets CD and is perpendicular to it Y. Okay, so now we've actually established two right triangles. First thing you want to do now for step 2, I would say that AX is perpendicular to CD, as well as the fact that BY is perpendicular to CD. What you can do with that is, if you drew two lines perpendicular from one base to the other, that's what's called the altitude. By the definition of altitude, you can say that those two lines are perpendicular to CD. Great, we've established that. Now, we can actually, on the third step, we can say that triangle ADX and triangle BCY are right triangles. We can now say triangles ADX and BCY are right triangles simply by the definition of right triangle. Okay, so we have at least that the hypotenuse is congruent in each right triangle. What else do we need? We either need a congruent angle, or we need a congruent leg, or something like that. Well, we can actually go on to say that AX is congruent to BY. How so, you might ask? let me get to that here. So AX is actually congruent to BY. How is that? Well, any two points from one parallel line to another are equidistant from the other line. So by that theorem, 2 points on a line parallel to another line are equidistant from the second line. That's kind of a long one, but that's what the theorem is, and there's really not a much better way to abbreviate it. So, by the theorem that 2 points on a line parallel to another line are equidistant from the second line. In other words, AX would be congruent to BY. Well, now we have the hypotenuse and a leg of that right triangle congruent to each other. So, by the hypotenuse leg theorem, or the HL theorem, we can say that triangle ADX is congruent to triangle BCY. That would be by the HL theorem. The hypotenuse leg theorem. So now that we've established these two right triangles are congruent, all that's left to conclude is that angle C is congruent to angle D by CPCTC. So angle C is congruent to angle D by CPCTC. Corresponding parts of congruent triangles are congruent. So let's go through this proof again. We were given trapezoid ABCD with AD being congruent to BC. That was given to us. From there, we can draw auxiliary lines, which will be the two altitudes of this trapezoid from A to CD and B to CD. And we call the points where the auxiliary line from A to CD meets X, and the line from B to CD meets it, called Y. We can go on to say that AC is perpendicular, AX is perpendicular to CD, and BY is perpendicular to CD by the definition of altitude. Next, we could say that triangles ADX and BCY are right triangles since they both have right angles in them by the definition of a right triangle. And then we can actually go on to say that AX is congruent to BY by that theorem that 2 points on a line parallel to another line are equidistant from the second line. This enabled us to conclude that triangle ADX is congruent to triangle BCY by the hypotenuse leg theorem, the HL theorem. And then finally, we could say that angle C is congruent to angle D by CPCTC. Corresponding parts of congruent triangles are congruent. So there is your proof that base angles of an isosceles trapezoid are congruent. All right. That's the only proof today. That's the worst of the lesson. Now, I'm going to draw another trapezoid here. We have trapezoid A, B, C, D. What we have now, we'll have points E and F. right here. What is EF? Well, we have trapezoid ABCD where, of course, AB is a base, CD is a base, they're parallel to each other. That means AD and BC are the legs, but what's EF? EF is the median. So, unlike a triangle, in a trapezoid, the median of a trapezoid joins the midpoints of both legs to each other. So point E is the midpoint of AD, point F is the midpoint of BC. So therefore, since this segment here, the median of the trapezoid joins the midpoints of the two legs of the trapezoid, EF is the median. And there's a two-part theorem about the median. The median, excuse me. Theorem. Okay. The median of a trapezoid so there's two parts to this. Part one is parallel to the bases. Part two, the length is equal to the average of the sum of the length of the bases. Alright, so the last theorem for today is that the median of a trapezoid is parallel to the bases. That's part one. So that means EF is also parallel to AB and CD. That's essentially what part one of this theorem is. So by that we can conclude that EF, the median, is parallel to AB, and then EF, the median, is also parallel to base CD. So that one's not so bad. But what about part two? Part two of this theorem states that the length of the median is equal to the average of the sum of the bases. So let's look at this particular trapezoid. If you wanted to find the length of EF, that means it's equal to half of the sum of the lengths of AB and CD. So EF, to find the length of that, would be equal to half times the quantity of the length of AB plus the length of CD. And I got some exercises where we're going to put this theorem into practice, particularly part two. Part one's pretty self-explanatory. Part two, though, that definitely requires some practice. So let me draw these trapezoids for us. I have 9 exercises that we'll get through. Let me move this a little lower so you can see what we're doing. Alright. Got trapezoids with medians. This is 9, this is X, this is 15. Alright? the goal of each of these 9 exercises is going to be to solve for x. Well, I think it's clear that 9 and 15 are the lengths of the bases. X is the length of the median, right? So how do we solve that? Well, the length of the median, in this case x, would be equal to half the sum of these two bases of 9 plus 15, which then would equal 1/2 of 24, which could only mean then half of 24, that x equals 12. So the length of the median in this case would equal 12. That wasn't so bad. I got 8 more exercises. What does the next one look like? Kind of reversed. Not my best work, but it'll suffice. Clearly not an isosceles trapezoid, but still a trapezoid nonetheless. Let's see what lengths they give us this time. We have 25 for the top base, x for the median, and then 13 for the bottom base. So yes, you can have trapezoids flipped upside down. But nonetheless, we need to find the length of x, the median, which is going to be equal to half the sum of the two bases of 25 plus 13, which means that's equal to half of 38, which could only mean then half of 38, that x equals 19. So the length of the median with length x is equal to 19. Different one yet. Now that looks too much like a parallelogram. Definitely not trying to draw a parallelogram. There, that's my best attempt at it. Let me draw the median here. So you can also have trapezoid sideways. You'll have that sometimes too. So this time the left base is x. The median is 11, and the right base is 7. Well, we still have to solve for x, but this time x is the length of one of the bases. That doesn't matter. What we're going to do then, the median has length 11, right? So we're going to take 11, we're going to set that equal to 1/2 times the sum of the bases, which would be x plus 7. So this time we have 11 equals half of the quantity of x plus 7. Well, I think we can clearly say we don't want to work with fractions. So what you probably want to do, multiply both sides by 2. You'll simply get x plus 7 equals 22, which would have to mean that x equals 15. So the length of the left base with length x would be 15. So sometimes the problems will take the form of needing to find the length of a base. Okay, different one yet. Another trapezoid this time with, we have it reversed again and sideways. We have x, 13, and 21. So the length of the smaller base is x, the length of the median is 13, the length of the bigger base is 21. Well, it's still the same process. The length of the median, which is 13, is equal to 1/2 the sum of the two bases, which would be x plus 21. So what I would do, multiply both sides by 2, you'll get x plus 21 is equal to 26, which should then just give you that x equals 5. So the length of the left base would be that x equals 5. All right, a little tilted trapezoid. We have a little tilted trapezoid here. Let's see what we get this time. Oh, they're spicing it up on us. So this base is 18. This median has a length of x plus 4. This base has a length of 8. Well, we still got to solve for x, but the median has a length of x plus 4, so that means we'll set that median of x plus 4 equal to half the sum of the two bases, which would be half of 18 plus 8, which would simply mean then that x plus 4 would be equal to half of 26. And we know half of 26 is 13, so you would get x plus 4 equals 13, which then means that x equals 9. So the value of x in this case is going to be 9. And I only have 4 more. We're already almost through it. Here's another trapezoid. If I could quit dropping crap. This time we have first base is x, second base is 10. I'm sorry, first base is x, median is 10, second base is 3x. So this time we have x in both places. Well, again, the median, which is 10, is still equal to half of the sum of the two bases, which would be x plus 3x. Which means then that 10 is equal to half of 4x, which half of 4x is 2x, so that would give you 2x equals 10, which could only mean that x equals 5. So the value of x that you're going to get is 5. Three more, then we're done. Finally, a more classic trapezoid. Let's draw the median. These last three are a little trickier. So the length of the first base is 2x minus 1. The length of the median is going to be 19. The length of the second base is 7x plus 3. Well, we still got to solve for x. Well, that length of the median, 19, is still equal to half the sum of the two bases. So that'd be half the sum of 2x minus 1 plus 7x plus 3. Which means 19 is equal to 1/2 of 9x plus 2. Well, again, I don't think anybody cares to work with fractions, not whatsoever. So multiply both sides by 2, you'll end up getting 9x plus 2 is equal to 38, which means that 9x equals 36, which would give you that x equals 4. So the answer you should get for this one is that x equals 4. Two more. Upside down trapezoid, no big deal. Draw that median. Okay. Well, let's see. The length of the top base is going to be 3x plus 2. The length of the median is going to be 2x plus 4. And the length of the bottom base is going to be 2x plus 1. So we have x on all three of them. Well, let's take the length of the median, 2x plus 4. 2x plus 4, that's going to be equal to half the sum of the two bases of 3x plus 2. Whoops, I'm not doing a FOIL. What am I doing there? 3x plus 2 plus 2x plus 1, which would simplify into 2x plus 4 equals half of 5x plus 3. Well, I think it's safe to say again, no one likes fractions. So multiply both sides by 2. You'll have to do the distributive property on the left if you do that. That should then end up giving you 4x plus 8 equals 5x plus 3. Which then to finish should just give you that x equals 5. So the value you're looking for with this trapezoid for x is that x would equal 5. And there's just one more problem, then we're done. Now this lesson isn't too bad. Trapezoids actually are pretty cool to work with. Last one, another sideways trapezoid. Gotta put me through the sideways junk. Okay. Let's see what we get for lengths this time. So the left base of the trapezoid is 5x plus 12. The median is just 5x. And then the right base is 3x. So those are all the lengths for your trapezoid. Well, that median 5x, you take that length of 5x, set that equal to half of the sum of your two bases. So that'd be half of 5x plus 12 plus your 3x, which would turn into 5x equals 1/2 times 8x plus 12. Well, you can either multiply both sides by 2, or since you have even numbers inside the parentheses, you can just distribute the half, which is what I'm going to do. That would give you that 5x would equal 4x plus 6, which just gives you x equals 6. So in the end, you should get that x has a value of 6. And that's it for this lesson. So that's really it for the quadrilaterals unit. Next lesson, we're going to start talking about inequalities in geometry and indirect proofs and different kinds of things. So, because up till now, we've been dealing with equalities in geometry and everything being equal. Well, the next 5 lessons, we're going to deal with inequalities in geometry. So, I hope everyone has a great night. Take care.